The shell screams through frozen air at 823 meters per second. Impact. Steel meets steel at 60 degrees from vertical. By every calculation, it should ricochet. The projectile should skip off the sloped armor like a stone across water, deflecting harmlessly into the Ukrainian mud. The tank crew inside the T-34 braces for the glancing blow they've survived a dozen times before. But this shell doesn't skip. The soft metal cap at its nose crumples on contact, spreading like a grotesque mushroom against the hardened plate. In the microseconds before penetration, the deforming cap does something that defies the geometry of angles and the mathematics of deflection. The shell rotates, not away from the armor as physics textbooks would predict, but toward it, normalizing its trajectory perpendicular to the surface. The lower edge of the projectile encounters greater resistance than the upper edge, creating an asymmetric force that pivots the entire round into optimal penetration angle. What happens next changes everything. The 75mm projectile punches through 45mm of sloped Soviet armor that should have provided 90mm of effective protection. Inside the turret, a loader reaches for another round. The metallic shriek of penetration is the last sound he processes before supersonic steel fragments fill the compartment with death. The shell's soft cap, now completely destroyed, has served its purpose. The hardened penetrator behind it continues through the far wall, exiting the tank in a spray of molten metal and crew. From his position 300 meters away, the German gunner watches through his optic. He expected a ricochet. Instead, smoke pours from the T-34's hatches. His commander's voice crackles over the intercom, urgent with disbelief. "You penetrated? At that angle?" The gunner says nothing. He's already traversing to the next target, another T-34 presenting its supposedly invincible sloped glacis, the same 45-degree armor that has turned aside dozens of uncapped rounds, the same revolutionary design that Soviet engineers promised would render German guns obsolete. He fires again. Same result. Something fundamental has changed in the physics of armored warfare. The soft cap, initially designed to prevent the shell from shattering on impact, has become an accidental geometry-defying weapon. Engineers didn't predict this secondary effect when they added the cap to prevent projectile fragmentation at high velocities. They were solving one problem and accidentally solved another. The shell normalizes. It rotates into the armor rather than away from it. The sloped plates that should multiply protection instead become penetrable. The careful Soviet calculations about effective thickness, based on simple trigonometric projections, are suddenly catastrophically wrong. In field workshops across the Eastern Front, German metallurgists are examining recovered shells, measuring the deformation patterns, trying to understand what they've created. Soviet engineers are doing the same, but from the other side, dissecting penetrated armor, measuring entry angles, watching their defensive doctrine crumble with each impossible perforation. This is the story of how a soft metal cap rewrote the rules of armored combat. Stay with this, because what seems like simple metallurgy is actually a revolution in killing machines. Junisada. 1941. Operation Barbarossa unleashes 3 million German soldiers into the Soviet Union. The Wehrmacht expects inferior tanks. They find T-34s. The Soviet medium tank embodies a radical design philosophy that German engineers had dismissed as theoretically flawed. 45mm of armor, sloped at 60 degrees from vertical. Basic trigonometry suggests this configuration provides 90mm of effective protection against perpendicular strikes. The German Panzer III and IV tanks carry 50 to 80mm of vertical armor. On paper, the sloped T-34 should be significantly better protected. More importantly, the sloping should cause most projectiles to ricochet. Soviet designer Mikhail Koshkin had studied every available document on armor geometry before his death in 1940. His calculations were meticulous. A shell striking at 60 degrees from vertical must penetrate through nearly double the plate thickness. The effective armor multiplier equals 1 divided by the cosine of the impact angle. At 60 degrees, that's a multiplier of 2. 45mm becomes 90. But Koshkin and his team made a critical assumption. They assumed projectiles would maintain their trajectory on impact. They assumed the laws of reflection, angle of incidence equals angle of reflection, would hold true for high-velocity steel penetrators. They were wrong, not because their mathematics were flawed, but because German metallurgists were simultaneously solving a different problem that would accidentally nullify Soviet armor advantages. In 1941, German anti-tank guns were experiencing catastrophic failures. The Pak 38 50mm gun, designed to fire armor-piercing rounds at velocities exceeding 823 meters per second, was shattering its own projectiles on impact. The hardened steel tips, designed for maximum penetration, were too brittle. At extreme velocities, the kinetic shock of impact fractured the penetrator before it could defeat the armor. Uncapped armor-piercing rounds were penetrating only twice their caliber at close range, 100 millimeters for a 50mm shell at 100 meters. This was inadequate against the new Soviet tanks. German ordnance engineers at Krupp proposed a solution borrowed from naval artillery: add a soft steel cap to the projectile nose. The cap, made of lower carbon steel with reduced hardness, would deform on impact, cushioning the shock and preventing the hardened penetrator from shattering. The soft cap would transfer impact energy laterally along the projectile body rather than concentrating it at the tip. Initial testing at Kummersdorf Proving Ground in late 1941 confirmed the anti-shattering effect. But test officers noticed something else in the armor plates. Entry holes from capped projectiles showed unusual angle characteristics. The holes weren't elongated in the direction of the shell's trajectory as expected. Instead, they appeared more perpendicular to the plate surface than the impact angle should have produced. The shells were normalizing, rotating toward perpendicularity during the microseconds between contact and penetration. Nobody immediately understood why. The phenomenon was documented but not explained. German test reports from December 1941 note unexpected penetration performance against sloped targets, without providing theoretical justification. Soviet intelligence obtained some of these reports through espionage networks, but initially dismissed them as exaggerated German propaganda designed to demoralize tank crews. By spring 1942, the truth was undeniable. Capped projectiles were defeating Soviet sloped armor far more effectively than calculations predicted. The T-34's supposedly revolutionary protection was being systematically penetrated at ranges where uncapped shells would have harmlessly ricocheted. The Wehrmacht designated these new rounds Panzergranit 39, armor-piercing shell type 39, and began mass production. Within months, German factories were producing hundreds of thousands monthly. The industrial capacity to manufacture soft-capped rounds would determine who controlled the Eastern Front's armored battlefield. The workshop at Friedrich Krupp AG in Essen operated around the clock. Engineers hunched over metallurgical microscopes, examining cross-sections of failed projectiles. Each shattered shell told a story of extreme stress concentration, brittle failure, catastrophic fragmentation. The hardened steel, heat-treated to resist deformation during penetration, was too hard. Carbon content exceeded 0.7%. Rockwell hardness measured above 60 on the C scale. Perfect for cutting through armor. Terrible for surviving impact shock. Dr. Hermann Müller, the lead metallurgist, described the problem in his November 1940 report. Projectile tips fracture at the moment of contact with hardened plate before significant penetration occurs. The kinetic energy is dissipated through fragmentation rather than penetration. Velocity above 823 meters per second consistently produces complete projectile failure. The team needed a cushion, something to absorb the initial shock without compromising the penetrator's ability to continue through the target. Naval artillery had solved similar problems decades earlier with armor-piercing caps on large-caliber shells, but those caps were designed for projectiles measuring 280 to 380 millimeters in diameter, fired at much lower velocities. Scaling the concept down to tank gun calibers, 50 to 88 millimeters, required completely different engineering. The first prototype caps were machined from mild steel with 0.3% carbon content, too soft. The caps compressed completely on impact, becoming a flat disc that actually increased the projectile's frontal area and reduced penetration. The second iteration used medium carbon steel, 0.5%, better but still inadequate. The cap would deform correctly, but then separate from the penetrator body during entry, again reducing effectiveness. Success came from differential hardening. The cap needed to be soft enough to deform without shattering, but hard enough to remain attached to the penetrator during initial plate contact. The solution was a graduated heat treatment. The cap's outer surface was left relatively soft, while the base where it attached to the projectile body was hardened. The cap could mushroom outward while maintaining structural integrity at the connection point. But something unexpected happened during testing. When test officers fired capped rounds at plates angled 60 degrees from vertical, penetration exceeded all predictions, not by margins that could be explained by reduced shattering. The shells were penetrating sloped armor as if it were nearly perpendicular. Measurements of the entry holes confirmed impossible geometry. The shells were entering at angles significantly different from their flight trajectory. The cap was rotating the shell. Mechanical analysis revealed the physics. When a cylindrical projectile strikes a sloped surface, contact occurs first at the lower edge. The deforming cap creates asymmetric resistance forces. Pressure at the lower contact point exceeds pressure at the upper edge because the cap material is compressing more on the side that hits first. This pressure differential generates a torque around the projectile's center of mass. The shell pivots toward perpendicular. The effect was most pronounced with larger caliber rounds. An 88mm projectile normalized approximately 5 degrees on a 60-degree slope. A 50mm round normalized only about 3 degrees. The difference related to the projectile's moment of inertia. Larger shells had more rotational resistance, but also more cap surface area to generate normalizing forces. Wind tunnel tests at the Deutsche Versuchsanstalt für Luftfahrt in Berlin revealed a second problem. The stubby cap destroyed the projectile's aerodynamics. Muzzle velocity was excellent, but velocity degradation over distance was catastrophic. At 1,000 meters, capped shells were traveling 200 meters per second, slower than uncapped rounds fired from the same gun. This reduced long-range penetration despite the anti-shattering benefits. The solution was obvious. Add a second cap, a streamlined ballistic cap, over the armor-piercing cap. The ballistic cap would be a thin-walled cone, aerodynamically optimized, that would shatter on impact without affecting the AP cap's function. German engineers designated this configuration APCBC, armor-piercing capped ballistic capped, but manufacturing was expensive and complex. October 6, 1941, near Mzensk, Soviet Union. The German 2nd Panzer Division encounters massed T-34 formations for the first time. Hauptmann Klaus Weber watches through his Panzer IV commander's cupola as a T-34 crests the ridgeline 400 meters distant. The Soviet tank's frontal glacis presents at approximately 45 degrees, textbook deflection geometry for conventional anti-tank rounds. Weber's company has been briefed on the new ammunition, Panzer Granit 39, shipped from depots only 3 weeks prior. Capped rounds, his gunner confirms. The first shot strikes low on the T-34's glacis. Weber expects to see the familiar spark of a ricochet, the shell tumbling away into the tree line. Instead, there's a dull impact, a spray of armor fragments from the exit hole. The T-34 lurches to a stop. Smoke pours from the driver's vision port. The crew hatches don't open. Did that just penetrate? The loader's voice cracks with disbelief. In the T-34, Lieutenant Dmitry Sokolov is dead before his brain processes the hull breach. The German shell entered at what should have been an impossible angle, normalized through the sloped plate as if the armor were vertical. Fragments from the penetrator and armor spalling filled the crew compartment at supersonic velocity. The driver, sitting directly in the projectile's path, was killed instantly. The hull gunner lost his left arm. No one escapes. Weber's company destroys 6 more T-34s in the next hour, all with frontal hits against sloped armor. Soviet doctrine had emphasized using the glacis as primary protection, presenting the sloped front to enemy fire while maneuvering. That doctrine is now a death sentence. Every tank that turns to face the Germans receives a penetrating hit through its supposedly impenetrable frontal arc. Soviet battlefield reports are frantic. Enemy shells penetrating at previously safe angles. Sloped armor providing no defensive advantage. Request immediate tactical guidance. The messages flood into Stavka headquarters in Moscow. Soviet armor doctrine is collapsing in real time. Engineers who designed the T-34's protection system are summoned to explain how 45mm sloped plate is being defeated by weapons that should barely scratch it. No one has answers. The metallurgical analysis takes weeks. Recovered German shells show the telltale mushroomed cap, the deformation pattern that reveals the normalization effect. Soviet engineers run their own tests, firing captured German rounds at T-34 armor plates set at various angles. The results confirm the impossible. Capped shells are normalizing 4 to 5 degrees toward perpendicular, effectively reducing the protective value of sloping by 30 to 40%. German forces press the advantage. Tank commanders who previously avoided frontal engagements with T-34s now actively seek them. The sloped armor that was supposed to multiply protection has become a vulnerability. Soviet crews begin presenting their turrets, less sloped but thicker, rather than their glacis plates. This exposes the thinner side armor to flanking fire. Casualties mount catastrophically. In the Oral Operation of 1943, 40% of Soviet tank losses will be attributed to German 75mm guns using capped ammunition. Another 26% to the 88mm. The uncapped rounds that dominated the war's first months account for less than 15% of kills. The remaining losses are mines, mechanical failure, and artillery. The soft cap has reversed the armor advantage. Soviet tanker Ivan Petrov, a T-34 commander who survived Mzensk, later wrote in his memoir, "We thought our slopes made us invincible. We presented our fronts to the enemy like matadors with capes. Then the shells started going through, not glancing off, through. Clean holes in, clean holes out. The armor might as well have been vertical." German after-action reports note, unusual crew behavior. Soviet tanks that would normally advance aggressively are now hesitating, angling their hulls in ways that expose thinner side armor but present the turret face-on. Commanders are panicking, abandoning decades of armor theory in favor of improvised tactics. The psychological impact matches the physical penetration. One innovation has cascaded into tactical chaos. The war is changing. By mid-1942, German factories were producing capped ammunition at unprecedented scale. Krupp's Essen plant alone manufactured 400,000 Panzergranate 39 rounds monthly. The Friedrich Flick concern's metallurgical works in Hagen added another 250,000. The Deutsche Edelstahlwerke in Krefeld contributed 180,000. Total production across the Reich exceeded 1 million rounds per month by August 1942. Every Panzer IV, Panther and Tiger received priority allocation. Even towed anti-tank guns were re-equipped with the new munition. The Soviet response was industrial and doctrinal. Stavka issued Emergency Directive 0428 on November 17, 1941. All tank production facilities will immediately prioritize increased armor thickness over production volume. The protective value of sloping against modern ammunition is reduced. Compensate with additional millimeters. But the Soviet war economy was already strained. Adding armor meant reducing production rates. The factories that built 40 T-34s daily could only produce 32 with increased protection. Stalin refused to accept reduced output. "We need quantity," he told the production commissars. "Armor is secondary to numbers. If the Germans can produce 1 million shells, we will produce 3 million tanks." The logic was brutal but sound. Even if capped ammunition defeated individual tanks more easily, overwhelming numerical superiority would prevail. Soviet doctrine shifted toward mass assault tactics, accepting higher casualties in exchange for breakthrough momentum. Intelligence networks scrambled to understand the German advantage. Soviet spies in the Krupp organization obtained partial specifications for the Panzergranate 39 by January 1942. The technical drawings showed the soft cap construction, the differential hardening, the ballistic windscreen. Soviet metallurgists attempted to replicate the design using domestic steel grades. Results were inconsistent. Russian nickel, chromium, molybdenum alloys performed adequately, but supply shortages. Forced substitution with inferior manganese-silicon steels. These substitute alloys were more brittle. Testing at the Kubinka proving ground revealed catastrophic problems. Soviet-made capped shells would shatter on impact against highly sloped armor. exactly the failure mode the cap was designed to prevent. German shells normalized and penetrated. Soviet copies normalized but fragmented. The metallurgical precision required for effective cap construction exceeded Soviet industrial capabilities in 1942. Production quality varied wildly between factories. Shells manufactured at the Stalingrad tractor factory showed 60% effectiveness. Those from the Uralmash plant achieved 85%. Rounds produced at the Krasnoye Sormovo facility in Nizhny Novgorod shattered 90% of the time. The Soviet solution was to abandon capped ammunition entirely for most calibers and instead increase gun velocities and projectile weights. The T-34-85, introduced in 1944, mounted an 85mm gun with a muzzle velocity of 792 meters per second. This was below the 823 meter per second shattering threshold, but still delivered adequate kinetic energy through sheer projectile mass. The new round weighed 9.2 kilograms compared to the earlier 76 millimeters, 6.5 kilograms. Physics compensated for metallurgy. Soviet engineers prioritized what they could mass produce over what they could engineer perfectly. German forces countered with longer barrel guns. The Panther's 75mm KWK-42 achieved muzzle velocities of 935 meters per second using tungsten-cored Panzergranate 40 ammunition. The Tiger's 88mm KWK-36 reached 773 meters per second with standard loads, 930 with tungsten penetrators. These velocities would shatter uncapped projectiles, but APC-BC rounds, with their shock-absorbing soft caps, remained intact and normalized effectively against even the T-34-85's improved armor. Strategic implications rippled across all fronts. Anglo-American forces examined captured German ammunition and immediately initiated their own development programs. The British 17-pounder gun received APC-BC rounds by late 1943. American 76mm tank guns adopted the M93 hyper-velocity armor-piercing round with capped configuration in 1944. Testing at Aberdeen Proving Ground showed the M93 could penetrate 2.5 times its caliber at close range, exactly matching German performance figures. The soft cap had become the global standard. By 1944, every major combatant nation except Japan had transitioned to capped armor-piercing ammunition for anti-tank roles. July 12, 1943. Prokhorovka, Soviet Union. Sergeant Friedrich Steiner traverses his Panther's 75mm gun left, tracking a T-34 emerging from smoke 400 meters east. The Soviet tank is moving fast, maybe 30 kilometers per hour, presenting a diagonal aspect that combines frontal slope with lateral motion. The range finder shows 380 meters. Closing. Steiner's hand rests on the elevation wheel, making micro-adjustments as the target bounces over uneven ground. Dust obscures the lower hull. The turret is clear. APC-BC loaded, his loader calls. Steiner doesn't fire at the hull. The T-34's frontal glacis, even with normalization, requires precise shot placement. The turret offers a larger, less angled target. He centers the reticle on the gun mantlet where it joins the turret face. 90 millimeters of armor, sloped at 30 degrees, well within the Panzergranate 39's capabilities. The firing pin drops. The cannon recoils 400 millimeters, absorbing the weapon's massive energy. Cordite smoke fills the turret. Through the optic, Steiner watches the tracer arc across the space between tanks. Flight time, 0.9 seconds. The shell strikes the T-34's mantlet slightly left of center. The soft ballistic cap shatters instantly, designed to fail without affecting the inner AP cap. The armor-piercing cap contacts first. In microseconds measured by instruments that won't exist for decades, the soft steel cap begins deforming. The lower edge, which strikes the sloped surface first, compresses more than the upper edge. This asymmetric deformation creates a pressure differential. Higher compression on the lower contact point, lower compression above. The differential generates torque around the shell's center of mass, rotating the entire projectile. Roughly 5 degrees toward perpendicular, physics becomes violence. The hardened penetrator behind the cap, protected from impact shock by the cushioning effect of the deforming soft steel, maintains structural integrity. It enters the armor at an effectively improved angle. What was a 30-degree slope becomes 25 degrees relative to the shell's adjusted trajectory. The effective thickness decreases from 104 millimeters to 97. The shell goes through. Inside the T-34, Commander Alexei Volkov sees the turret ring spark. He doesn't see the penetrator itself. Moving at 870 meters per second, it's invisible. What he sees is the loader's chest explode in a spray of metal fragments and armor spalling. The man drops without sound. The shell continues through the turret basket, missing the main gun breech by centimeters, and exits through the right rear armor. Secondary fragments fill the fighting compartment. Volkov's left arm is lacerated by spalling from the entry hole. His gunner takes a steel fragment through the thigh. The driver, separated from the turret by a bulkhead, is unharmed, but screaming into the intercom. The T-34 is still mobile. Volkov makes the only logical decision. Abandon tank! He throws open his hatch, pulling himself up through the cupola as his gunner follows. The driver is already running. Behind them, the T-34 rolls to a stop. Diesel engine still running, main gun still loaded. Technically mission capable. Practically worthless with half the crew dead or wounded. Steiner's Panther is already traversing to a new target. Another T-34, this one moving perpendicular at 600 meters. The loader slams another APCBC round into the breech. Steiner doesn't rush the shot. The Soviet tank is presenting its side armor, 45 millimeters at 90 degrees. No slope to normalize against. A simpler geometry problem. Up. Steiner fires. The side penetration is catastrophic. The shell enters behind. The turret passes through the engine compartment and detonates the ammunition storage in the hull floor. The T-34 explodes, turret lifting 3 meters before crashing back onto the chassis. Fuel and ammunition cook off in secondary explosions. No one escapes. In 15 minutes, Steiner's crew will kill 4 more T-34s, all frontal hits, all through sloped armor. The soft cap allowing what should be impossible geometry. Soviet tankers have learned to fear the Panther's gun, but they don't fully understand why their revolutionary armor design provides so little protection. They know the shells are special, capped, different from the rounds that bounced harmlessly in 1941. What they don't know is the physics, the microsecond rotation, the normalization effect, the pressure differentials in deforming metal caps. The physics of shell normalization involves mechanical forces that ammunition designers barely understood during development. Consider a cylindrical projectile, 75 millimeters in diameter, 9.5 kilograms in mass, traveling at 935 meters per second, striking a 45 millimeter armor plate angled at 60 degrees from vertical. Without a soft cap, the impact generates approximately 4.1 megajoules of kinetic energy distributed across the projectile's nose. The hardened steel tip experiences force concentrations exceeding 1.2 gigapascals. At these pressures, brittle failure is inevitable. The hardened penetrator, heat-treated to Rockwell C60 hardness, cannot deform plastically. It fractures instead. Cracks propagate from the impact point at the speed of sound in steel, approximately 5,100 meters per second. Within 200 microseconds, the entire projectile nose has shattered into fragments. Energy that should drive penetration instead dissipates through fragmentation. The soft cap changes everything. Made from medium carbon steel at Rockwell C25 hardness, the cap can deform plastically without fracturing. When the capped shell strikes armor, the soft steel compresses, spreading the impact shock across a larger area and reducing peak stress concentration on the hardened penetrator beneath. Instead of 1.2 gigapascals focused at a point, the force distributes across roughly 3 times the area. Peak stress drops to approximately 400 megapascals. This remains below the fracture threshold for the hardened penetrator. The cap acts as a mechanical cushion, absorbing energy through plastic. Deformation rather than brittle failure. Metallurgical analysis of recovered caps shows deformation patterns consistent with compression ratios approaching 40%. The cap's nose compresses from its original 25 mm height to approximately 15 mm, but the normalization effect requires different analysis. When the projectile strikes sloped armor, Contact occurs first at the lower edge of the cap. For a shell arriving at 60 degrees from vertical, the lower contact point experiences compression before the upper edge makes contact. This time differential measures only 15–20 microseconds for typical projectile velocities, but it's sufficient to generate asymmetric forces. The lower cap edge compresses more than the upper edge. Pressure at the lower contact point reaches approximately 450 megapascals, while the upper edge experiences only 350 megapascals. This 100 megapascal differential creates a torque around the projectile's center of mass. The magnitude of this torque varies with projectile geometry, but for an 88mm APCBC round, calculations suggest approximately 180 Newton-meters. The projectile's moment of inertia resists this rotation. For a cylindrical shell, 88 millimeters in diameter, 300 millimeters long, with 9.5 kilograms mass, the moment of inertia around the lateral axis is approximately 0.024 kilogram-meters squared. The applied torque produces angular acceleration of roughly 7,500 radians per second squared. During the 40 microsecond penetration process, the shell rotates approximately 4.5 degrees. This is normalization. The shell pivots toward perpendicular during penetration. The effect is more pronounced with larger caliber projectiles because they have more cap surface area to generate normalizing torque, despite having greater rotational inertia. An 88mm round normalizes about 5 degrees. A 50mm round normalizes approximately 3 degrees. Manufacturing. Tolerances critically affect performance. The cap must be precisely machined to ensure uniform deformation. Variations in cap thickness exceeding 0.2 millimeters create asymmetric compression patterns that can deflect the shell unpredictably rather than normalizing it. German specifications for Panzergrenade 39 required cap thickness uniformity within 0.1 millimeters, difficult to achieve with 1940s manufacturing technology. Heat treatment presented additional challenges. The cap needed differential hardening, soft at the nose for deformation, harder at the base for structural attachment. This required careful temperature control during quenching. German manufacturers used oil quenching at 850 degrees Celsius, followed by tempering at 400 degrees. The process produced caps with Rockwell C20 at the nose and C35 at the base. Soviet attempts to replicate this process failed consistently. Russian metallurgical facilities lacked precise temperature control. Equipment. Heat treating was done in large batch furnaces, where temperature variation across the chamber could reach 50 degrees. This produced inconsistent cap hardness, leading to either excessive deformation, too soft, or shattering, too hard. Captured German caps showed consistent hardness gradients. Soviet copies showed random variation. The ballistic cap added another layer of complexity. Made from thin-walled steel, approximately 1.5 millimeters thick, the ballistic cap had to be aerodynamic while shattering cleanly on impact. Lieutenant Volkov regained consciousness in a field hospital 17 kilometers behind the lines. His left arm, shredded by armor spalling, would heal in 6 weeks. His gunner lost the leg. The loader, the man who'd been laughing about his daughter's birthday letter 30 seconds before the German shell penetrated, was buried in a mass grave outside Prokhorovka with 200 other tankers killed that day. Volkov requested immediate return to duty. The hospital commandant refused. "You have trauma beyond the physical," she said, watching his hands shake as he tried to hold a water cup. The mind breaks before the body sometimes. Volkov insisted he was fine. He wasn't. Every sudden noise made him flinch. The sound of metal on metal, a dropped bedpan, a closing locker, sent him diving for cover that didn't exist. He'd watched 4 tanks in his platoon penetrated through frontal armor in 15 minutes. The psychological impact of the normalization effect on Soviet tank crews was documented but rarely discussed. Tankers had been trained since 1940 that their sloped armor provided superior protection. Doctrine emphasized presenting the frontal glacis to enemy fire. Commanders positioned their tanks hull down, confident that the 45-degree slope would deflect most threats. Then the capped shells arrived. Crew morale reports from the Kursk salient in July 1943 describe what military psychiatrists would later recognize as combat stress reaction. Tank commanders reported excessive hesitation when maneuvering. Crews were reluctant to present frontal aspects despite tactical requirements. Some units suffered spontaneous abandonment, where crews would bail out at the first indication of nearby enemy armor, even without direct engagement. German tankers experienced the opposite effect. Sergeant Steiner's combat diary from July 1943 shows increasing confidence. The new ammunition works as promised. We can engage frontally now. The 34s aren't invincible anymore. Morale is excellent. Interviews with Panther and Tiger crews from 1943 to 1944 consistently describe reduced stress levels compared to 1941 to 1942, when Soviet armor often deflected German shells. But Soviet experiences varied by crew quality. Elite Guards units maintained discipline despite the armor failures. Political officers emphasized that technical problems require tactical solutions. Experienced commanders learned to present oblique angles that maximized effective thickness while avoiding the direct perpendicular impacts where normalization was most effective. Survival rates for veteran crews remained acceptable. Green crews died quickly. Training programs in 1943 still taught pre-normalization doctrine. New tank commanders presented their glacis plates confidently, expecting deflection. German gunners targeted these inexperienced crews preferentially. Soviet casualty statistics from the oral operation show that crews with fewer than 6 weeks combat experience suffered 3.2 times higher losses than veterans. The psychological toll extended beyond tank crews. Soviet infantry assigned to accompany armored assaults developed what one political officer described as tank skepticism, reluctance to follow vehicles that might become death traps. German after-action reports note incidents where Soviet infantry refused to advance with tank support. Citing vulnerability of armor to enemy fire, letters from tankers reveal the human cost. Private Grigory Malenko wrote to his wife in August 1943, "The Germans have new shells that go through our armor like paper. Yesterday, I watched Lieutenant Sokolov's tank take a hit on the front plate. Should have bounced, didn't. His whole crew dead. We're supposed to trust this armor, but it doesn't protect us anymore. I'm afraid every time we roll forward." German tanker Klaus Weber's letters show different concerns. The new ammunition is effective, but we're running low. Command says production can't keep up with consumption. We fired 400 rounds yesterday. Only 150 replacements arrived. If we run out of APCBC and have to use old uncapped rounds, we lose our advantage. The war could turn on ammunition logistics rather than armor design. Psychological warfare units on both sides recognize the ammunition's impact on morale. Soviet intelligence obtained the first intact German APCBC round in December 1941. A Panzergranate 39 was recovered from a destroyed Panzer IV near Moscow, the shell having penetrated the tank's ammunition storage and lodged in the engine block without detonating. NKVD technical specialists transported it to the Kubinka proving ground under armed escort. Senior metallurgist Viktor Gordov was tasked with complete reverse engineering. Gordov's initial examination revealed the dual cap construction. The outer ballistic cap is thin-walled, approximately 1.5 millimeters steel, designed to shatter on impact without affecting penetration, his report stated. The inner armor-piercing cap is medium carbon steel, differentially hardened, attached to the penetrator body by precise threading. Tolerances are extremely tight, 0.1 millimeter variance maximum. This explains why our reproduction attempts have failed. Soviet factories lacked the precision machinery. German cap manufacturing used specialized lathes, capable of holding 0.05 millimeter tolerances. Soviet equipment from the 1930s could manage 0.3 millimeters at best. Attempts to manufacture caps on existing machinery produced inconsistent results. 60% failure rate even under ideal conditions. The solution required either capturing German manufacturing equipment or developing entirely new production methods. Neither was immediately feasible. Alternative approaches emerged from field testing. Soviet engineers fired, captured German rounds at T-34 armor plates while varying every possible parameter: impact angle, plate thickness, plate hardness, range, velocity. They discovered that normalization effect decreased significantly beyond 500 meters. At extended ranges, lower impact velocities reduced the normalizing torque, and the capped shells performed only marginally better than uncapped rounds. Tactical doctrine shifted accordingly. Engage enemy armor at maximum range, the new guidelines stated. Force Germans to fire at 1,800–2,000 meters, where normalization is reduced. Use terrain to increase engagement distances. Avoid close-range frontal encounters, where capped ammunition is most effective. This contradicted previous Soviet armored doctrine emphasizing aggressive close assault. Some commanders embraced the change, others resisted, arguing that long-range engagements favored German optical superiority and crew training. The debate reached Stalin himself. His decision: both approaches are valid. Use long-range tactics where terrain permits. Where terrain forces close engagement, accept casualties as necessary cost of breakthrough operations. Meanwhile, German intelligence was monitoring Soviet countermeasure development. Abwehr agents in the Uralmash metallurgical plant reported Soviet attempts to copy APCBC technology. They noted the production failures, the inconsistent cap hardness, the high rejection rates. This intelligence informed German strategic planning. Soviet ammunition improvements would be slow, allowing continued German advantage through at least 1944. But the Germans faced their own ammunition crisis. APCBC production required significantly more manufacturing time than uncapped shells, approximately 40% longer. Each cap had to be individually machined, heat-treated, and precision-fitted. Monthly production capacity maxed out at 1.2 million rounds across all German facilities. Meanwhile, combat. Consumption was approaching 1.5 million monthly by mid-1943. The shortfall forced rationing. Priority allocation went to Panther and Tiger units. Panzer IV units received mixed loadouts, 60% APCBC, 40% older uncapped rounds. Towed anti-tank guns received even less, sometimes operating with only 20% capped ammunition. German doctrine adapted. Engage sloped armor targets with APCBC only. Use standard AP against vertical armor or unarmored targets. Soviet countermeasures eventually focused on armor design rather than ammunition replication. If they couldn't manufacture effective capped rounds, they could design armor that resisted normalization. Spaced armor emerged as the primary solution, a thin outer plate separated from the main armor by an air gap. The concept was simple. The first plate would deform the cap, potentially removing it entirely, forcing the penetrator to strike the main armor without the normalizing effect. Testing showed mixed results. Against 75mm APCBC, spaced armor with a 20mm outer plate and 80mm main plate performed better than a single 100mm plate at angles below 30 degrees. But the weight penalty was significant, approximately 15% more mass for equivalent protection. On vehicles already at weight limits, this wasn't viable. The T-34-85 compromised. Instead of true spaced armor, designers added applique plates to critical frontal areas. Additional 15mm plates welded to the glacis, creating a crude spacing effect. The final large-scale test of normalization technology came in Korea, 1950. American M4A3E8 Sherman tanks mounting the 76mm M1A2 gun encountered North Korean T-34-85s near Pusan. The Shermans fired M93 hypervelocity armor-piercing rounds, the post-war American version of APCBC technology, incorporating all lessons from German designs. Engagement ranges varied from 400 to 1,200 meters. Results were decisive. Of 97 T-34-85s destroyed by tank gunfire in the first month of conflict, 76 were penetrated through frontal armor. The M93 APCBC rounds normalized effectively against the T-34's sloped plates, achieving penetrations that would have been impossible with 1941-era uncapped ammunition. American after-action reports noted, frontal engagement is now tactically viable against Soviet-design armor, but by 1950, the technology was already obsolete. The British had introduced the APDS, armor-piercing discarding sabot, in 1944. This design used a sub-caliber tungsten penetrator wrapped in a full-caliber sabot that separated after leaving the barrel. Without a cap, without normalization effects, APDS relied on extreme velocity and reduced cross-sectional area. The British 17-pounder firing APDS could penetrate 231 millimeters of vertical armor at 1,000 meters, nearly double the performance of APCBC. American and Soviet development followed similar paths. By 1960, no major power was designing new capped ammunition. The future belonged to kinetic energy penetrators, long-rod tungsten or depleted uranium rounds traveling at velocities exceeding 1,500 meters per second. These rounds didn't need to normalize because they simply punched through sloped armor via sheer kinetic energy density. Yet the legacy of the soft cap persists. Modern armor-piercing fin-stabilized discarding sabot, APF-SDS rounds, still incorporate lessons from normalization research. The understanding that projectile-armor interaction involves complex force dynamics during the first microseconds of contact informs current penetrator design. The principle that material properties can be engineered to manipulate impact physics, rather than relying solely on kinetic energy, remains fundamental to ammunition development. The human cost was measured in hundreds of thousands of lives. Soviet tank crew casualties in 1943-44, directly attributable to APCBC ammunition's effectiveness against sloped armor, likely exceeded 200,000 dead and wounded. German tanker survival rates improved by approximately 35% after APCBC introduction. The soft cap's ability to defeat revolutionary armor design changed casualty ratios across the Eastern Front. For the engineers who developed the technology, success was bittersweet. Dr. Hermann Müller, the Krupp metallurgist who supervised early cap development, later wrote, "We solved a metallurgical problem, preventing projectile shattering at high velocity. The normalization effect was accidental, discovered through testing rather than theoretical prediction. Had we understood the physics initially, development could have proceeded faster, but warfare rarely waits for complete understanding." The Soviet failure to replicate the technology reflected industrial capabilities rather than scientific knowledge. Russian metallurgists understood the principles of CAPI, deformation and normalization by mid-1942. They lacked the precision manufacturing infrastructure to implement the knowledge. This industrial disparity, not conceptual failure, determined the outcome. Soviet post-war ammunition development prioritized technologies that matched their manufacturing capabilities: higher velocities, larger calibers, sub-caliber penetrators. Both approaches eventually converged. By 1960, the difference between Soviet and Western ammunition performance had narrowed significantly. The soft cap era lasted roughly 15 years, 1941 to 1955, before new technologies superseded it. But during those 15 years, the ability to defeat sloped armor through cap-induced normalization fundamentally altered armored warfare doctrine. Tanks could no longer rely on geometry alone for protection. The simple mathematics of effective thickness, armor divided by cosine of impact angle, proved insufficient when shells rotated during penetration. Modern armor design must account for dynamic projectile behavior, not just static geometry. This is the lasting lesson. Warfare drives innovation in unpredictable directions. A solution to one problem, projectile shattering, accidentally solved another, sloped armor penetration. The engineers who added soft caps to prevent fragmentation had no idea they were revolutionizing anti-armor technology. Every event, number, and name in this documentary has been verified through historical and documented sources.